This lesson is going to be the last one in part 1 of Redox. The next lesson will be starting on part 2 of Redox. So this lesson has to do with redox stoichiometry. Basically, we are going to take two concepts that you are already familiar with and we are going to bring them together into one thing. So these are Stoic questions. So we are doing Stoic from Chem 20, right? That's not changing. We're going to do some unit analysis. The new piece, I guess you could say, is how you are generating your equation, right? So these are redox questions. We need to make sure that we are writing redox equations. Hopefully you have figured out by now that double replacement and neutralization reactions are never redox because we don't actually have changes in charges. And so you should not be writing a double replacement reaction for a redox Stoic question. Unfortunately, a lot of you guys tend to do that because you just read the question and you want to immediately generate that equation. So it's important to recognize that on these redox Stoic questions, you need to, I don't want to say most of your work comes before you get to the Stoic, but really most of your work does come from before you get to the Stoic. So what you want to do is, if you think back to those steps we talked about in writing a redox equation, right? We want to list all the species. Once we've listed everything, we want to figure out, we want to assign OA and RA, right? Hopefully by now, you started to become a little more comfortable with recognizing what's an OA and what's an RA. So step 3 is go to your data booklet and find the SOA and the SRA. Right? And when we find them, we're going to write out those equations. Once we have those two equations, we're going to make the electrons the same and combine the two equations. Once we do that, we now have our balanced equation, and now we're just going to do some Stoic, right? So now we get to do some Stoic. Right? So that's kind of the easy part, hopefully. Doing the Stoic, because you've been doing the Stoic for well over a year now. So really the big chunk of work comes in generating that redox equation, and then there's just that Stoic at the end of it. Okay, so just going to do one example. We've done examples on how to write equations. We've done Stoic in Chem 20. We reviewed Stoic. You have, I don't want to say lots of questions, but you have a decent number of questions for you to practice inside of your practice booklet. So first example we have here. So in a redox titration, 12.5 mils of 0.08 mole per liter potassium dichromate was used in an acidic solution to oxidize 10 mils of tin-2 ions to tin-4 ions. The volume of potassium dichromate used was just sufficient to oxidize all the tin-2 solution. Calculate the concentration of the tin-2 ions in the solution and what color change indicated the endpoint of this titration. So when we do redox Stoic, we often do titrations. Normally, if we were at school, we would actually do a titration. Okay, so let's walk through what you're going to do. So we are going to start by listing everything we have. So we have potassium dichromate. So really that means we have potassium ions and we have those dichromate ions. Okay, what else do we have? We will have water, and we have water because these are solutions. It then tells us that it is an acidic solution. The fact that it is acidic means that we also have hydrogen ions. Okay, you're going to find a lot of our redox titrations require hydrogen ions, and that's because a lot of half reactions in our data booklet require hydrogen ions, which is why we need to have that acid there, okay? And then what are we doing? We are going to oxidize tin-2 to tin-4. So although it talks about tin-2 and tin-4, if you read that, it says that we are going to oxidize the tin-2 into the tin-4. So although tin-4 is written here, when I'm listing things out, I don't want to list that because this is a product, it's not a reactant. And I don't want to list things that are products because then I may pick an SOA or an SRA that isn't actually a possibility, okay? So these are all the species we have. So now we are going to go to our data booklet and we're going to look at that data booklet and we're going to determine what's an OA and what's an RA. So first thing we listed was a potassium ion. So a potassium ion is over here on this side. Remember we said everything on the left side of our data table was an OA? So that means this is an OA. Okay, next thing we need to find is this dichromate ion. So dichromate is way up here at the top. It requires hydrogen ions. This is why, like I was saying, we need to have it as an acidified solution, because if we didn't have that acid, I couldn't pick this because I would be missing a piece. Okay, so that means dichromate is also an OA. Okay, then we have water. We've talked about water before. We've said water could either be an OA or it could be an RA. Okay, then we have hydrogen ions. So although it was in the half reaction involving the dichromate, it's also in this table on its own, right here, kind of in the middle of your page, and it's also over on the OA side. Okay, last thing we have is tin 2. If you remember back to earlier on in the lesson, tin 2 was one of those that could be both, right? It could be an OA or it could be an RA. If you didn't remember that, you could go to your data booklet and you would see that you find it on both sides, right? So here's tin 2 over on this side as an OA. And then, where is it as an RA? It's definitely on here somewhere. Oh, right here, not much higher than it, okay? Here it is over on the RA side. So it could be an OA or it could be an RA. Okay, so now that we've assigned everything as potentially being an OA or an RA, we need to figure out what's the strongest oxidizing agent and what's the strongest reducing agent. So OA-wise, we are deciding between K+, the dichromate, the water, and the hydrogen ion. So to find the strongest, remember we said the SOA was up at the top, so we start up here and we start scanning. First thing we hit is that dichromate. So my SOA is going to be the dichromate. So this is going to be my SOA. So while we have our eyes on that half reaction, we're going to write out what it is. So it was that Cr2O7 2- aqueous plus 14H plus aqueous plus 6 electrons to give us 2 Cr3 plus AQ and let's see, 7 waters. Okay, so there's my SOA. Now I need to find my SRA. I should really already know what it is because the question told me that we were going to oxidize tin 2 into tin 4, but I definitely can check in my data book, right? My only potential RAs are water and tin. So remember, for RAs, we start at the bottom and we work our way up. So we start here, we're going, still haven't found one, still haven't found one. Oh, here's the tin. That's the first one I hit. So that means tin is going to be my SRA. Okay, so my second half reaction is going to be that SN2 plus AQ turning into SN4 plus AQ plus 2 electrons, right? And that's coming from my data booklet. I'm not making these things up. These are in my data booklet for me to obtain. So now that I have them, we want to combine them. To combine them, we need to make electrons the same. If this is 6 and this is 2, we're going to have to times everything in this tin equation by 3 so that our electrons are actually going to cancel out, right? So now when we look at this, this is going to cancel with that. So what we're left with is going to be that balanced chemical equation. So we are going to have the Cr2O7 2- 14H plus. Sorry, I'm going to be lazy and I'm just going to copy paste this because there's a whole lot of superscripts and subscripts and they get a little annoying to write after a while. Well, if I can move it, there we go. Okay, so we have that plus those 3 tin 2 ions giving us, hold on, there we go, the 2 Cr3 plus and 7 waters, along with the 3 tin 4 ions. Let's see if I can fix that formatting so it all goes across the same line. Okay, so I don't want to say that's most of my work, but I'm probably going to spend more time doing this and generating the equation than I'm actually going to spend doing the stoich, right? The stoich is the more straightforward part. So potassium dichromate is what we were given. I need to recognize that dichromate is the same as potassium dichromate. We've just gotten rid of the spectator ion, right? So I know that for that dichromate, it was 0.01250 liters, and I was given a concentration of it as 0.0800 moles per liter. Okay, and then what else were we given? We were given for the tin 2 that we had 10 mils, so 0.01000 liters. And we were looking for the concentration of that, right? So this is where we're now just going to do basically Chem 20 stoich to determine what the concentration of that tin 2 was. So we need to get moles per liter, moles of tin 2, so we can start with our ratio. So we can say 3 moles of SN2 plus, and we can put that over 1 mole of that dichromate. Okay, we need to eliminate the unit moles of dichromate, right, because that's not actually in our thing, so we can times by the concentration. Oh, I'm in superscript mode, and I meant to do underline. Having difficulties. Here we go. And that's going to be over liters. Okay, so now we can eliminate that unit moles of dichromate. These are the liters of dichromate. We need to get rid of that. To get rid of that, we're going to times by the volume of dichromate. So we're going to times by 0.01250 liters. Right, that is going to cancel our liters. If you really want to, you can definitely put this over 1. If you like everything to have a top and a bottom, you can do that. Last thing we need to do is introduce the per liter of the tin 2. So then we're going to do times, and we're just going to flip over that volume. So we'll put a 1 on top, and on the bottom, 0.0100 liters. Okay, so plug this into our calculator. So 3 times 0.08 times 0.0125 divided by 0.01, and we should be getting 0.300 moles per liter as our concentration. Okay, so last part of the question asked you, what is the color change going to be? So what you are going to find when we do redox titrations, right? And when you think about titrations, historically the titrations you have done have all been acid-base titrations, right? And we've always added an indicator to tell us when to stop our titration, or we use like the pH meter. In redox reactions, those don't work anymore because we're not creating a neutral solution, right? We are transferring electrons. However, what you find is a lot of these ions have colors associated with them. So if you go to page 11 of your data booklet, you'll notice that you have a table back there. It's called Color of Common Aqueous Ions. Generally, you're going to find that when we do redox titrations, we deal with ions that have colors associated with them. So we don't have to add an indicator to tell us when it's done, because we already kind of have some natural color changes that are going to happen as our reaction occurs. So the example we were just working on, we had dichromate, hydrogen ions, tin 2, Cr3 plus water, and tin 4 plus. So when we look in here, Dichromate is here and it is orange, right? So I know from this that we have the dichromate, which I'm just going to do this in typing so it's a little prettier looking than my lovely writing. So we know that this dichromate is orange. Okay, hydrogen ions, for the most part, you should be familiar with the fact that hydrogen ions are colorless. You've used HCl, sulfuric acid, a million times. There's no color, but you definitely could check this table. There are no hydrogen ions on here. That means they are colorless. Okay, our next reactant was the tin 2. There's also no tin in here, so that means it has no color. When we look at our products, water, which you know is colorless, we have Cr3 plus and SN4 plus. So chromium 3 is a blue-green to a green, right? So let's just consider it to be green, mainly because our concentrations are 0.08, and this one was 0.3. I guess it was a little higher, but you could either say green or blue-green. It really doesn't matter. And then tin 4 wasn't on there, so it has no color, okay? So we have orange and we have blue-green. So a lot of times you guys would look at this and you would say, okay, a color change then is orange to blue-green. But what you actually find is that is not going to be the color change. Okay, so why that's not going to be the color change? What you generally find when we do redox titrations is where we place things. Generally, what we do is whichever is the colored reactant, we tend to put that into the burette. Okay, so into the burette, wait, that's not my arrow, I want an arrow. Into the burette, we are going to place the colored species. And usually what we try to do is in our flask, we try to put the one that is not colored. Okay, sometimes they're both colored. If they're both colored, we're going to put whichever one has the lighter color. Or not no color or not color, no color or lighter color. Okay, the reason we do that is if you think about the question we were just talking about. If I start with the orange stuff down here and I start adding stuff to it, that orange is going to slowly start to turn green. But I'm still going to have a mix of orange and green. And so there's just a whole lot of colors happening in this flask. The other challenge tends to be, a lot of times when I do a redox titration, if we forget to add acid, right? Because if you think about that question, it said an acidified solution. Sometimes you guys forget to add acid. And usually when you actually do the titration, the way you know you forgot is as soon as you add from your burette, your flask turns this like, I don't want to say chunky brown, but it just goes like this weird color where you're like, whoa, what is that? And then usually you can fix it by quickly adding acid to it before you go significantly further. So how this would work in the particular example that we are talking about, if you think about the two things we have a tin 2 solution and we have a dichromate solution. So we would actually be placing the tin 2 solution down into the flask because then my flask starts colorless. And I would be placing that dichromate solution up into the burette so that my burette is starting orange and this is starting colorless. Then what I would see is as I start to add the dichromate and we start to produce products, we said that the products had a blue-green color. So I would see that as soon as I added some of this dichromate, the color in here would go from colorless to blue-green. But that wouldn't be telling me I was done. It would just be telling me that I had started to produce products. And what I would find is that the more dichromate I add, the more blue-green the solution would become. But then I would reach a point where I added some orange and I then saw orange in my flask. When I see that orange appearing in my flask, which is quite different from blue-green, I would know that at that point I've added an excess of dichromate and I need to stop my titration. So when you are doing redox titrations, the color change you are looking for to tell you it's done is actually going from product color to reactant color, because that then means your reactant is present in excess. So my final color change, going back to this question, would be that I would see that the blue-green turned orange. And as soon as I saw orange, I would stop. So redox titrations, so for redox titrations, the end point is when you see reactant color remaining in your Erlenmeyer. Okay, it's not about seeing the product color, because you're going to see that almost instantly, right? As soon as I produce it, I'm going to see that. But if you think about a titration, you never finish a titration after adding 0.1 mils, right? Usually it's at least like 7 to 15 kind of thing, okay? So that is how your redox titrations work. The stoich part is exactly the same as what you always do. Generating the equation is different, and figuring out the color change is kind of backwards from what we usually look at. So I didn't do an example of this, but you have some in your booklet, I think, where they give you some trials. Please remember that when you are doing multiple trials in a titration, you should normally be eliminating one, right? If I gave you 4 trials and you went to the lab and you did 4 trials, usually there's one that isn't like the other, and we're going to eliminate it. So either we're eliminating one because the color is different, or we're eliminating one because the volume is different from the others. If they're all very close, then absolutely you can use them all. But generally, please remember, when you are given more than one trial, you're given like 3 or 4, usually you are going to eliminate one of them, okay? So that concludes the first half of redox. I'm not sure exactly if we are going to do a midway check-in on redox, or if we're just going to do one at the end of the unit. Please make sure that you are checking your emails and that you are checking the announcements on the D2L shell, because all that information does get posted there, okay?